So without further ado, let me introduce the first speaker today. This will be Roser Valenti from Goethe University in Frankfurt. We'll talk about the many phases of alpha ruthenium trichloride graphene heterostructures. So please, Roser.
Yeah, thank you very much, Urban. And in fact, thank you very much to all organizers for the opportunity to participate into this today's workshop. Today in my talk, I will present our results on theoretical modeling of alpha-ruthenium trichloride on graphene heterostructures, and I will discuss the richness of the many phases of these heterostructures and also the comparison with now running experiments on these systems. First and most importantly, I would like to acknowledge my collaborators in this project, David KITP, who is a PhD in Frankfurt, Steve Winter, who just moved to Wake Forest in North Carolina, Kira Riedel and Sananda Biswas, both postdocs in Frankfurt, and Ying Li, who is now a professor in China. Last but not least, Johannes Knoller from Munich, and we are being funded by the German Science Foundation. So my talk has two parts. In the first part, I will concentrate on the electronic properties of alpha-ruthenium trichloride on graphene heterostructures. And from what we learn out of these studies, I want then in the second part of my talk to focus on the importance of the magnetoelastic coupling in alpha-ruthenium trichloride and on estimates and how we understand the role of this coupling in the properties of the system. So let me start with the first part. And the idea here is what happens when we bring two systems that are very different together on an heterostructure. What do we expect from this building of the heterostructure? So on the one hand, we want to consider alpha-ruthenium trichloride, which is a two-dimensional van-der-Waals mod insulator with a charge gap of about 1 electron volt. And this is a very intensively studied material because of its magnetic properties. So it's a KITF honeycomb material candidate. The strongest interactions are of KITF type. And on the other hand, we want to consider graphene, which is a two-dimensional Dirac semiconductor. In the following slides, let me first show you a short review of what properties we understand on ruthenium trichloride bulk in order then to see how we can modify these properties when we bring together this heterostructure. So in fact, ruthenium trichloride is a system which is intensively being investigated because of two, I would call it two seminal papers done in the past. The first one is the work of Alexei Kitaev, where he introduced what we now know as the Kitaev model. So this is a nearest neighbor Ising a bond-dependent model on the honeycomb lattice, which is exactly solvable. The ground state is a spin liquid, and it has fractionalized excitations of Majorana type. The second important work in this field is the work of George Jackley and Ginyard Kalulin, where they basically developed a recipe on how to have this type of model realized in a real material. And from there, I think that there was an explosion of work done on studies of materials where one could have and find out this type of physics predicted for the Kitaev model. So one of the most intensively studied materials, as I was mentioning, is alpha-ruthenium trichloride, which is a system that consists of layers of honeycomb lattice where we have ruthenium that is basically in this, basically in the corners of the honeycomb, and it fulfills in principle all the conditions that we need for a Kitaev interaction. However, as we know, materials are not perfect. They have distortions. They have, in fact, many other effects coming into the description of its properties that may induce interactions other than the interaction we want to fulfill. And in fact, we know by now that the description, the magnetic description of this system of alpha-ruthenium trichloride is not only given by a strong KITF interaction, but it also has other anisotropic spin interactions that play a role in the description of the properties of the system. One of the important part of the interaction is what we call the gamma interaction. So for instance, if you consider being yourself in this bond in an SZ-SZ KITF interaction, the gamma contribution would be for these two nearest neighbors SX, SY plus SY, SX. There is also small gamma prime term, which would be for the same bond, then to have terms like SZ, SY and SZ, SX. So moreover, we have a small contribution of Heisenberg terms, nearest neighbor and third nearest neighbors. And when you consider all these basically set of interactions, one can describe the properties of the systems. For instance, the fact that at low temperatures, the system is not a spin liquid, but it orders, it has long-range magnetic order in a zigzag way. And in order to convince you that the description of this system is not only KITF, but also these other anisotropic interactions, let me just flash here some experimental measurements on these materials. So on the right, I'm showing the experimental measurements. So this is, for instance, inelastic neutron scattering experiments on the ordered phase, where one nicely sees these magnon excitations due to the ordered phase, but there is a very strong region of continua of excitations, which is not present in a typical Heisenberg-like material. And this is, in fact, the nature of these excitations are being strongly discussed, whether they are Majorana excitations or what kind of excitations they are. And such a model with these various anisotropic interactions is able to describe these observed in elastic neutron scattering experiment. This is, for instance, exact diagonalization calculations for this type of model Hamiltonians. The same is for observations, for instance, of shifting of finite temperature spectral weight, that it's a consequence of these anisotropic interactions, and this can also be described by such a model, for instance, here by using finite temperature Langshor's measurements. And a third important feature of this material is its behavior on the magnetic field, where there is a hierarchy of high field excitations that are also a consequence of these anisotropic terms. And here, in fact, in the last years, there is a measurement that has been the center of discussion for this material, which is the observation by the group of Yuji Matsuda in Tokyo of quantized thermal Hall conductivity on the magnetic field. But what I want to do today, because I'm going to build structures for this system, is mostly concentrate myself on aspects like strain effects, because I'm going to make a heterostructure between two systems where there is a strong lattice mismatch. That means that there is going to be some effects of strain in ruthenium trichloride as well as in graphene, although we expect that the effects in ruthenium trichloride are much stronger. So let me show you in this slide why it's so important if we introduce a strain in this material. And what I'm showing is basically perturbation theory calculations of the magnetic interactions as a function. So when you apply perturbation theory on the Hubbard model, where T are the hopping matrix elements. So here I'm showing the important hopping matrix elements in ruthenium trichloride. So basically the nearest neighbor type of hybridizations that one can think of. This is ruthenium, ruthenium and chloride. So we basically I define three basic ones. This is interaction through the chlorine, while these are direct DD interactions. And what I want to show here by using these analytic expressions for the magnetic interactions is that very small changes in this hybridization between the ruthenium, so basically small changes in these hopping parameters due to the change of this angle, introduces huge changes in the magnetic interaction. So I can go, if I am, for instance, in the 90-degree configuration, where I have an important KITF, but also a very strong gamma contribution, we can go by changing the angle into a region where the KITF interaction is a dominant one. So we want to make use of these features now when we study these heterostructures with graphene. But what I want to show to you is when I'm going now to bring these two systems together, it's going to be a win-win situation for both, for ruthenium trichloride, but as well as for graphene. Because depending on the work function of ruthenium trichloride, I'm going to expect that there will be a charge transfer between ruthenium trichloride and graphene. So I'm going to basically dope graphene. And that will mean that one is going to expect that the conduction properties of graphene are going to improve. So let's see what happens now when we bring these two systems together and we form an heterostructure, where we are going to expect, as I was mentioning, effects of strain in this system, as well as doping, so charge transfer. So of course, the first way to try to understand what happens here is by doing an ab initio density functional theory simulation of this system. So basically, the idea is to take slabs, superstructures of these two systems, bring them together, and then test various different slabs. Which of those is the one that is energetically most favorable? And here I'm showing two of the possible slabs that we considered in order to find which slab is the one that is energetically most favorable. And what you can see here already is that by bringing these two systems together, because there is a strong lattice mismatch between the graphene layer and the ruthenium trichloride layer, I'm going to have effects of strain on the ruthenium, mostly on the ruthenium trichloride, because it's more soft than graphene. And where I want to focus your attention to is in fact into this hexagonal cell, because this is the cell where we find the system to be most stable. And in this cell, ruthenium trichloride basically sort of expands. So what I get is that the distance between ruthenium atoms gets larger. And this is going to be important because I'm going to get rid of some, basically some terms, some interactions that are detrimental for a pure KITF type of description. And this is basically the side view of this heterostructure. So now when we calculate with these heterostructures, basically what we find out is that there is an important charge transfer between the layer of graphene and the layer of ruthenium trichloride. So graphene gives charge to ruthenium trichloride. So what we end up having is a hole dope graphene and an electron dope ruthenium trichloride. And this has also been observed experimentally, that there is this important charge transfer, and basically it's happening here at the interface. Moreover, if we look at the electronic structure of this heterostructure, here what we observe is at the K point, where we used to have the direct point of the graphene, now graphene is hole dope. So here is our Fermi surface, and the ruthenium trichloride bands form basically almost flat bands around the Fermi level. And what one can distinguish is that there will be two types of Fermi pockets. At the K pocket, we expect to have whole pockets of graphene, and at the gamma point, we expect electron pockets of ruthenium trichloride. So this is the theoretical prediction. And there are right now quite a few labs that are in fact realizing devices of these heterostructures. And here I'm showing the device of the group in Stuttgart, Burkhardt and Klaus Kern group. And basically what they form is they sandwich alpha-RuCl3 and graphene in layers of hexaboronitride. And here are basically the gold electrodes in order to be able to measure resistivity in this heterostructure. And their measurements show the following. So here are the measurements from Stuttgart, and here are the measurements by Hendriksen and collaborators. Basically, they reproduce the same results. So what we see here is a column map of the resistance, and you see that there is in fact, unequal whether the voltage is negative or positive, what is telling us that we do have, in fact, holes that are doing the transport in this in graphene, and that, in fact, the conduction improves because of this charge transfer to the insulating lattice. So basically, this confirms this type of prediction. Moreover, the group of Stuttgart also performed Shundikov-de-Haas van-Alphen oscillation measurements. So here I'm showing the magnetoresistance, the longitudinal
Can I ask you a question, Roser?
Please.
Sorry to interrupt. I don't know what the protocol is for this, but
no, please, yes.
The 2 slides back where you showed the DFT prediction for the charge transfer, it looked like quite a lot. No, that one.
This one.
That one, yeah. It looks like I always have a little bit hard time. It looked like a large doping. What would be the? Can you say what the predicted 2D carrier density in graphene would be for that?
So what you want to know is how much charge transfer we are having, right?
Yeah, electrons per square centimeter.
I do have this number a few slides later. It's not that much. I mean, the picture, of course, looks a lot because this depends on, in fact, which ISO value we are plotting. I just chose this ISO value because it was very much representative of showing that the charge transfer is mostly happening at the interface, but I have the number a couple of slides later.
Okay, I was just looking from the right-hand panel. It looks like it's, a fairly large distance away from the K point.
The surface is large.
Yeah. You are looking here, you mean?
Yeah,
right?
Exactly. I'm looking at the area of the circle around the K point. Looks like a, substantial fraction of the zone, but sometimes these plots can be deceiving. I don't know. So
yes, indeed. I mean, in fact, this is the range of hybridization. What you are looking now, it's how much these two systems are hybridizing.
No, I'm not even asking about that. Just the distance, the radius of it. There's the point where you have the cone coming out like this, right? And just literally, what's the Fermi wave vector, away from K, measured away from K? It looks like a circle. Yeah. Just that carrier density, pi kf squared over 2 pi squared. Times I get
at the back of my mind, I don't have it, but I can give you the number. Let me just give you the number. Yeah, I don't have it in this as you would like. I just what I give you is the number of electrons per.
Yes.
Is this okay? So the number of electrons is about minus 0.064 electrons per ruthenium chloride unit. It's small.
That's in the graphene.
Yes, so in the graphene, it's going, exactly, the graphene is going to get discharged as holes, and the ruthenium trichloride is going to get discharged as electrons, exactly.
Not sure that's small.
It's small, yeah.
Well, per unit still, I don't know of ruthenium trichloride. I'm just wondering as a 2D carrier density.
Yeah, I mean, it's small if you think about doping the system with integer or half integer electron, but in terms of gating, that's pretty large.
It sounds huge, yeah. Right. Like beyond, that's what I'm asking. Is it within or beyond the range of gating?
Exactly. I think it's beyond the gating. Because
beyond the gating, and this for sure. So maybe the better picture to see that is this one here, where you see the conduction and that you increase, in fact, rather considerably the conduction in graphene. So here would be basically the conductivity that you would measure for graphene, And basically here you have in these units how much you improve with this charge transfer. Maybe this number is more helpful, but I can convert into what you wanted later on, this charge, if you want.
Yeah, I don't know. When I see that, if you show those kind of plot in ordinary graphene, normally the conductance minima is associated with the charge neutrality point.
Yes.
And you're doping away from it. But with that carrier density that you showed, I would have thought you couldn't reach the charge neutrality point by gating. So then I don't understand what the minimum, if you see that minima, I would have thought it means that either you have a minima for a totally different reason, although it kind of looks like the graphene minima, so it makes me think that one doesn't have that much charge transfer. I don't know, I'm trying to understand the consistency of those things. That's what I was,
okay.
Why I was asking.
Yeah. Okay, I can bring later on maybe more experiments that are being done right now where they, so for instance, recently Ken Burch has been trying now to determine better this charge transfer, and their claim in fact is that so the charge transfer is really very much larger than what you obtain by doing any other type of doping in these materials, either by molecules, but I don't have orders of magnitude, and you want an order of magnitude. This I cannot answer.
Yeah, you can just go on. I don't want to derail you too long. So
I can.
I ask, since you won the previous slides, very quick question.
Yes.
You said that the band for ruthenium chloride is very flat.
Yes. Yes.
So, but it's still below the, or it's
yes.
just.
So you see, yeah, it's rather flat, but still has a little bit of dispersion, and you can see it here in this blow up, where we blow up just to show that there are it's flat, but there is still a small dispersion, and it builds some. In this case, it's an electron pocket. So it's still the charge
but still dispersive.
It's rather localized, but still you expect a little bit of itinerancy. So maybe I should blow up more these bands, these flat bands. There is some small, but there is dispersion. And in fact, I think it's in the group of, yeah, right. This, no, Yang et al. Yang et al. This work is very recent from Dmitry Basov and collaborators, where what they have been also trying to check about how local is this charge in ruthenium trichloride, whether it's, they seem to find it rather local, but still you could expect some small itinerancy. So, more questions?
Just want to comment on the carrier density again. So you said it's 0.06 electron per unit cell. That's converted to 10 to the 14 per centimeter squared. And typically, if you do gating, I think 10 to the 13 would be huge. So 10 to the 14 is definitely beyond what gating can.
That was I just tried to estimate it. Makes sense. Yeah.
Okay. So I can check these numbers a little bit more rigorous later on and put it into the chat. Shall I continue, or are there more questions?
I have one more question.
Please.
Yeah, I was wondering how much is a strain in graphene? You mentioned that.
Oh, I'm going to show it to you. I was trying to go into that. Let me go there. So, but let me just show maybe this one more slide about these measurements, because what I wanted to point out about these measurements is that the frequency of these quantum oscillations is already telling us that there is an increase in the charge carriers, and moreover, the fast Fourier transform of these spectra, of the amplitude of these spectra, is clearly showing the presence of two Fermi pockets, which is these two Fermi pockets that I was mentioning to you. So these, in fact, at least the experimental measurements corroborate the presence of these small, but they are there, these pockets. And one more aspect that I would like to just mention is the fact that the temperature evolution of this fast Fourier temperature, fast Fourier transform amplitude of the Shubnikov-de-Haas-Van Alphen oscillations is not monotonous, as one would expect, but it shows this non-monotonous behavior at around 8 Kelvin. And tomorrow, Johannes Knoller, in his talk, he's going to talk about precisely how to understand this damping of the Shubnikov-de-Haas-Van Alphen measurements at low temperatures by making use of an effective KITF Kondo lattice model. So stay tuned, because Johannes will then try to show you how, in fact, one can understand the behavior of this damping. And here I basically want to continue now. Yes.
Just because you mentioned again, I think I missed it because I was thinking about the other thing. That what are the two pockets? Is one supposed to be in graphene and one in ruthenium trichloride? Is that the?
So the two pockets, one is here, basically. So we have, these are hole pockets near the K point. And then there are electron pockets around the gamma point. And one of them, so these pockets, so the hole pockets of the kappa, sorry that I didn't put the picture here, they basically build so pockets following the symmetry of the hexagon, while these pockets here, these electron pockets, are more one-dimensional type. So this is the Fermi surface that this.
So this is really from hybridization between the,
yes.
the bands. Okay.
Yes.
Great.
Yes.
Okay. Thanks.
Very, very much. These bands are very much hybridized. Yes. Okay. So tomorrow, Johannes will continue, in fact, with the description of these features. And I want now to go to this question that I was asked about the strain. So let me now concentrate on ruthenium trichloride, what happens to ruthenium trichloride in terms of strain and doping that we just commented a little bit. So the strain that that happens in this system, so as I was showing to you, of course, this comes now from our simulations, but what we saw is that there is an important tensile strain. And let me show you in the next slide that what it produces is the following. Because it's tensile, ruthenium go apart of each other. So I'm getting rid of this detrimental hybridization, which is in fact responsible for this gamma interaction. And here I'm showing the results. So this would be bulk alpha ruthenium trichloride, which has an important KITF interaction, but also an important gamma interaction. By straining the system to this construction of the heterostructure, the KITF interaction gets more dominant, and the gamma interaction, in fact, is reduced. So, in other words, this heterostructure, in fact, is going to the direction of having basically ruthenium trichloride described by almost KITF, nice KITF without other interaction terms. And there has been, in fact, a few studies of considering now the doping, because as we were discussing, there is doping in the ruthenium trichloride, even if the charge, the itinerancy is small. So if we now just take into account this new KITF model with some doping, there has been now various, in the past, various works trying to understand the possible phases of this type of models. And here I'm showing, for instance, the phase diagram that was obtained by Hayart and collaborators, where they considered a slave boson formalism to investigate basically a doped Heisenberg KITF model. And this is the charge I was, that's why I was trying to find the number. By considering this charge, this transfer, so in the case of ruthenium trichloride, it would be the electrons that we bring there from the graphene. And then we would bring the system into this region of possible P-wave superconductivity. And in fact, tomorrow, Johannes will talk a little bit more about this possibility of P-wave superconductivity in the system that could be maybe induced by applying a bias voltage. So by trying to bring the system, in fact, more into this direction. So I think in this sense, these heterostructures offer the possibility of getting new phases in these materials, and in fact exploring phases that otherwise in the bulk are very difficult to reach. And now if I have time, I don't know how much time I have, but if I have some 5 or 6 minutes left.
Yeah, that's perfect. Yeah.
That's fine. Okay, so let me now go into this question of strain, because after doing this work, we realized that it would be important to understand better this interaction between the lattice and the spin degrees of freedom. And for that, what we did is the following. So, of course, you can apply strain in your material either by constructing an heterostructure, as we did here, but also the simplest way of straining your material is first to think about hydrostatic pressure. But the problem with hydrostatic pressure, and these are experiments that have been done some years ago, and we also did simulations from ab initio, is that if you apply hydrostatic pressure, you basically favor precisely this type of hybridizations. And at the critical pressure, basically the system just distorts and forms singlets of nearby ruthenium atoms. So basically you go completely away from these KITF limits. And this is the conductivity experiments by Martin Dressel and collaborators, where they find that at about 0.9 gigapascals, the corresponding phonon splits, and there is then this phase transition. However, there is a third way of applying strain in the system, a third way in the sense heterostructures or application of hydrostatic pressure. We can think of applying uniaxial pressure. And in fact, this type of uniaxial pressure, where you have your layers of ruthenium trichloride and you apply the pressure, sorry, the uniaxial pressure along the z direction. So here what I'm showing is from going into compressive strain. So you see what's happening then to your system. If you apply the pressure along the z direction, then the planes of ruthenium trichloride are going to experience a type of also expansion, which is in fact the direction we would like to go, which is a direction that we know where we are going to promote KITF type only interactions. And the tensile strain, which would be just bring away the planes, you are inducing in the plane of ruthenium trichloride a kind of compressive strain. So you can very nicely see these different cases by doing ab initio calculations, and you can see precisely what I was describing to you now in terms of these graphics, where I show how the angles, ruthenium chlorine, ruthenium changes when we press. This would be the uniaxial strain, or we go away. This would be the positive uniaxial strain, and the same is about the distance of ruthenium and the lattice constants. But now what we want to do with that is, because we have from ab initio all these structures at different strains, we can now investigate how the coupling interactions, how the exchange interactions change as a function of this strain, as well as how much also the G factor changes, because we are changing very much the environment of ruthenium. So this is now the compact form of all the interactions in this, all the magnetic interactions in this system, where here you recognize the gamma, the Jagodzinski-Moria, the KITF, all the terms that are important. And now what we can do is to, indeed, what I wanted to go to is calculate the magnetoelastic coupling in the system by making use precisely of the fact that we have all these uniaxial strain dependent interactions, so we can obtain the corresponding magnetoelastic couplings for each one of these interactions as a function of looking at the slopes or calculating the slopes of these curves. And what I would point out too is what we observe that it's very interesting is that when you apply when you look at the changes in your parameters as a function of this uniaxial strength, this gamma prime interaction, basically this slope becomes extremely important. So it's telling us that this term is going to play an important role in these effects of straining the system. The same happens also with the KITF. Now the question, of course, is this is all simulations. How good are these simulations? So how can we compare with experiment? And this is my last slide. So there is one measurement that we can, where we can test these predictions for the changes of our parameters as a function of strain, which is the magnetostriction. So the magnetostriction, what it measures is the changes of your C parameter as a function of magnetic field. So these are in fact experiments from the Dresden group, Gas and collaborators, Anja Volter and Bernd Büchner, where they measured this magnetostriction as a function of magnetic field. And this is now a magnetic field applied along the, basically parallel to the plane. And what one observes, let me go to very small temperatures, that this magnetostriction is negative, and it suffers an important change when we reach the magnetic field where the long range order is suppressed in this material. So the lattice is responding very strongly to the magnetic field. So we can now calculate that. So this would be the theoretical way of calculating magnetostriction, where we have now these magnetoelastic couplings, and the derivatives of the magnetization with respect to the couplings, we can also numerically estimate them. And this is what theory gives us, so what these models that I was showing to you, that is able to describe, in fact, this very strong response of the lattice due to the magnetoelastic coupling to the magnetic field. And the nice thing about doing these simulations is that we can disentangle which contribution is the one that is most important for this effect. And what we see is, in fact, that gamma prime, this is the most important contribution for describing this effect here. And with that, I'm coming to the end of my talk, where in the first part, I hope I could show to you that alpha-ruthenium trichloride on graphene has many phases, and one expects, in fact, in this system, many possible new phases. So on the one hand, we have the increase in conduction in graphene due to the doping, the hole doping, also due to the strain induced on the ruthenium trichloride. We are changing drastically the interactions in the system, and what our prediction is that we bring the system more near to the KITF limit. And I hope that tomorrow Johannes can show you that this prediction could be confirmed by experimental measurements. What about unconventional superconductivity? One could maybe reach this region also with these materials. And there are recently also experiments showing plasma polaritons basically happening at these excitations happening at the interface of the system. These are the experiments of the group of Basov. And the last part was about the magnetoelastic coupling, where we, with this work, what I wanted to show to you is that this is a very, the coupling of the lattice with the spins in ruthenium trichloride is extremely strong. And the properties of the system respond, in fact, in a very delicate way to this magnetoelastic coupling. And with that, I would like to thank you for your attention, and sorry if I took more time than the given. So, and I'm ready for questions.
Thank you, Roser. Thank you.
Yeah, thanks for this nice talk. So I'm sure there are more questions.
I have a question as well, if possible.
Sure.
Yeah. Hi, Roser. My question is about the direction of the strain you use in your calculations. So here you have heterostructure, and I expect that the strain obviously changes in plane. Is there a reason why you use the strain along the z-axis?
Oh, for the second one. So, okay, in the heterostructure, indeed, because the ruthenium trichloride has to accommodate to graphene. And the bonding in ruthenium trichloride is in fact more soft than the bonding in graphene. So ruthenium trichloride, in order to accommodate, indeed you have that you are straining the along the AB direction. In the second part, you are doing exactly the same. Even though I apply pressure, uniaxial pressure along the Z direction, so what happens, you apply pressure, and this guy just blows up along the A and B direction.
You conserve the volume.
Yes, because you are, exactly. And this, in fact, the difference between these two cases is that this is more homogeneous because you are basically guided by all your substrate, while this one, because you are applying this uniaxial strain, you will have directions. One direction that is more, let's say, will be more affected than another direction. And this probably one can see it in this picture here. In this picture here, where you see that the A and B direction get differently affected, or you can even see it here when I plot. There is a different affected of the A and B direction to this uniaxial strain. So it's a different effect on the lattice, on the ruthenium dichloride.
Do you expect pneumatic effects to play a role here too, in the plane?
Oh, Amalia, this is a good question, but I haven't looked at it from the point of view of pneumaticity in this system. So what you are saying is whether, okay, so this material here, I am in a C2M symmetry, okay? And moreover, when the system orders, it's a zigzag order where you have broken the C, so it's basically a C2 state. Now, what pneumaticity would you expect? Maybe now I put the question to you.
Well, I know also twisted graphene has pneumatic phases, so I just wonder if you expect something to be induced in this type of system as well. Just a general question.
Yeah, I haven't thought about that. I think it's an interesting question to pose, but I haven't thought about having these effects here. It might be interesting to look at.
Thank you, thank you.
Thank you.
Two people have raised their hands, so Natasha Perkins and then Sasha Chernychev.
Rosa, I have a question. When you were showing the values for the couplings in the second part, for example, the dependence on the strain, these values for KITP interaction and for gamma were very large, like 40 something, and yes.
Yes, yeah. So this is the slope of the KITP interaction. So what I'm showing here, that's why I put the tilde. So you see the KITP, I'm sorry, I didn't spend a lot of time. The KITP interaction and the gamma prime interaction are these dots here. For every value of the strain, let's say at -2 strain, we have a KITP interaction, which is about -11 millielectron volts. While when I'm going at 2 positive, I have a KITP interaction of about -9.5. But what is very strong is the slope, is basically the variation of the interaction with the strain.
So it's a derivative, basically. Okay.
It's a derivative, yes, yes. And the same for
gamma prime. It was very surprising. Okay.
Yeah, of course. These are derivatives. That's the tilde. Okay. The tilde. Yeah, no, for sure.
Okay, fine. Thank you.
Yeah, I guess it answered half of my questions because I also took this picture as the decrease of both K and gamma prime.
Yeah, sorry.
Yeah, no, so the left plot though shows that the G factors become more. Am I reading it wrong again? They're becoming more free electron-like, and maybe...
So here, the G factor, when you go into this tensile strain, so basically this is how this is affecting. So basically you are sort of doing like a compression in ruthenium trichloride. And basically what you're getting is more, let's say, more symmetric octahedra. And that's why your G factor gets less anisotropic.
So for I think in the next on next slide, you had the phase transition in experiments. I think next second to the last. Yeah, this one. So clearly, as you pointed out, the data shows effects which are associated with the phase transition, with the ordering.
Yes.
So, yes. Is your theory also does it also contain the ordering to some magnetic state, or?
Yes, of course. These simulations. So basically, these simulations here are done by this is the ordered state. So that exactly by considering the model, which the model itself has a phase transition at 6 Tesla. So the model contains this order and the disappearance of the order at 6 Tesla. So okay. This is contained in the model. And the way we calculate that is we have these magnetoelastic couplings that we just I just showed in the previous slide how we obtain them. And this term here is calculated again with EV calculations on the spin model.
Thank you.
Yeah. Of course, because it's exact analyzation calculations, we have finite size effects. That's why you see these roundings and not this nice sharp phase transition. But yes, the model shows also this phase transition.
Okay, perhaps we have time for one more short question. For those who have still raised their hand and would like to ask question, Rosa, I don't know how long you will be available, but
I'm still here, so.
Yeah, so perhaps after the next talk, we have a 30-minute break.
Okay.
So if you are around, perhaps we can have a more.
Yeah, I'll be around.
Awesome. So yeah, Gangshen was the next person who had raised their hand. Please.
Oh, thank you very much. So in the quantum oscillation, the interpretation was in terms of some kind of hybridization between graphene and ruthenium trichloride. I'm wondering, when you cool the system down to imagine the system develop magnetism, ruthenium trichloride develop this magnetism, does the magnetism impact on the oscillation? And
this is precisely the question that tomorrow, Johannes. That's why I don't want to interfere into the talk of Johannes. Johannes is going to talk precisely about that.
Okay.
So stay tuned tomorrow because Johannes is going to pick precisely this question. What about the ordering and the effect, how the ordering may affect, in fact, the conduction in graphene, the measurements that are being done, how do we interpret these measurements? So this is, I leave now for Johannes. Mm-hmm. Is that okay?
Okay.
But yes, I mean, let me just answer on my side just shortly. Indeed, there are two scenarios. If I try to now understand these measurements here, one scenario is in fact the fact that we know that the bulk ruthenium trichloride orders at about 7 Kelvin. So this is the reason why you also see these anomalies. So that could be because of a spin scattering, because the ordering is setting in, that you are having these features. But an alternative explanation is we have been seeing that there is this very strong hybridization between ruthenium trichloride and graphene. And one could, in fact, consider that this is a consequence of this strong hybridization. And then a model that is very suitable to describe this type of phenomena is the Kitaev-Kondo lattice model. But this is what Johannes will present tomorrow.
Mm-hmm. Okay,
and
thank you.
We can discuss later on if you want.
Yeah, I would be happy to discuss more.
Yeah, for sure. So
okay.
I stop sharing.
Yeah, on that note, let's thank Rosa again for this awesome talk. Yeah.